Alright, good day, students. Now, just a quick recap of what we would have looked at so far in terms of electricity. We first mentioned that electricity is the movement of electric charge through a conductor, unending conductor, right? And from there, we introduced the term known as electric current, where electric current is the rate at which electric charge flows through that conductor, giving us a general formula that it is I is equal to Q over T, right? And then we went in to look at the term known as voltage, also potential difference, which is the term which refers to the amount of energy needed to push this electric charge across a component, right? So we realize that it gives us a formula that V is equal to E over Q, meaning the amount of energy needed to move each unit of charge across a given component, meaning across a battery, across a bulb, across an ammeter, any bit of component, right? We also introduced the term known as EMF, which is the total voltage, which refers to, gives you the total amount of energy needed to move charge around a complete circuit. Now, today what we're going to be looking at is a term known as electrical power, right? Now, power in the essence of it is a term that comes up in physics in every single topic, right? Once we need energy to be converted or work to be done, we realize that we have a term known as power. So in this case, electrical power is the amount of energy that is converted per unit time, right? And as we know that energy is needed to move the charge, so we're going to realize that electrical power is the amount of energy needed to energy converted per unit time. Now what we notice is that P is equal to E over T. P is equal to E over T, meaning power is equal to energy converted per unit time, or energy divided by time. And in the formula for potential difference, we realize that given that energy divided by unit charge, we can rearrange that formula to see that energy is equal to the amount of electrical charge multiplied by the voltage, right? So E is equal to Q times V. Good? Now, given that we know that E is equal to Q times V, it means that we can substitute it into this formula, right? We can substitute it into the new derived formula for power, which is P is equal to E over T. And we end up with QV over T. P is equal to QV over T. And so it means that we need the terms of, we need potential difference, we need electric charge, and we need time in order to find power. Now, suppose we don't have all those quantities, but what we want to realize is that Q over T is also equivalent to something that we know. That Q over T is actually equivalent to electric current. So therefore we can substitute that into our formula. So it works down to be that power is also equivalent to the amount of electrical current multiplied by the voltage, right? And that will be equal to our power. And power therefore still has the same SI unit of watts, right? Watts is the SI unit. If the numbers are large, you'll be converted into kilowatts. Good? So that's the SI unit of power and the formula there. Now, the next term that I must quickly introduce to you is the term known as resistance. Right, so the term resistance, it sounds more like when you're talking about resisting to do something or a bit of friction. Good, so in this case, we want to understand that electric current is the movement of electrical charge. So in a conductor, so if there's something opposing that movement of electrical charge, that opposition is therefore referred to as the resistance. It's like looking at a river flowing with water. Good. And as the water flows downstream, there are boulders in that river. and the boulders can prevent the water from flowing freely and allow the water to run around it, and so on. The water has to find other paths to flow. So it's in that case we want to relate it to the movement of electrical charge. That if there are components inside that conductor that can prevent the free movement of electrical charge, is known as resistance. Now, resistance follows two main factors that influences resistance. One, it can be the length of the conductor, or two, it could be the diameter of the conductor, meaning the large amount of spacing through which that charge can flow. Good. So a textbook definition for resistance can go as follows: is that resistance is the measure of the opposition provided to an electrical current. All right. So the measure of the opposition. Opposition meaning trying to oppose the flow of electrical current, and therefore it works out to be the ratio of the potential difference across a conductor to the current through it. So it's a ratio of the potential difference to the current flowing through that conductor. So therefore it gives us this equation that R is equal to V over I, right? So it's a ratio, and you know a ratio is another way of saying a division. So it's the ratio of the voltage to the current flowing through it. Now this formula can therefore be rearranged and in order for us to find voltage. And this equation V equals IR, in other words, can be summed up as Ohm's law, right? And Ohm's law states that at constant temperature, the potential difference across the ends of a conductor is directly proportional to the current through it. So basically it's saying, I'll repeat it, at constant temperature, the potential difference across the ends of a conductor is directly proportional to the current through it. So it is therefore saying that as current flows through any current carrying material, any conductor, once the nature of that conductor doesn't change, once it doesn't heat up or anything like that, once the temperature doesn't change, then there will be a constant flow of that electrical charge, meaning that the voltage doesn't change. So in other essence, if we were to plot that on a graph, we're going to end up with a straight line. That if you compare the current and the voltage, that it gives us a straight line. So it means that this represents an ohmic material. Good? Because the gradient of this straight line represents the constant R. Good? So because V is directly proportional to R, then this is your constant. So it's the gradient of this line represents the resistance. Good? Now, in some cases, if that line isn't a straight line, it therefore means that your resistance is increasing, either because you're increasing in temperature, or the they're increasing in high currents, right? If the current is also increasing, that these are results of it. Now, one of the things next thing that we're going to introduce to you is what happens in a current carrying conductor. We would have introduced to you the series circuit and the parallel circuits. These are two of the components through which current can flow. Now, we looked at what happens in a series circuit, where we know that series circuits where all the components are connected one behind the other. And we mentioned that one, the current is constant, that the current never changes throughout the entire circuit. So it means that the total current delivered by the power source, in this case it's 6 amps. If the total current delivered by the power source is 6 amps, it means that the total current passing through each of the components in that series circuit is also the same value. So the total current is equal to the current at the first component, which is equal to the current at the second component, which is equal to the current at the third component. Right? So each of these are also 6 amps. Good? So IT is equal to I1, equal to I2, equal to I3. Good. Second point in a series circuit is that the voltage varies, that the voltage isn't always the same. The voltage varies, the voltage is shared throughout the circuit or among each of the components in the circuit. So it means that the total voltage delivered is going to be split up, but they're going to all add back up to the same value. So for instance, if our 6 amps of current is supplied there, let's say it delivers 9 volts of voltage. It delivers 9 volts. What is happening now is that the 9 volts is actually divided up among the three items or the three components in the circuit. In this case, it's 3 bulbs. And each of the bulbs are going to utilize 3 volts as the current passes it. So 3 volts, 3 volts, 3 volts. Now when we add them all together, V1 plus V2 plus V3, it should be equal back to the total voltage supplied there. So in essence, when we say total voltage, we're referring to EMF. Alright? EMF is the term used there when we're referring to the total voltage. Good? In the case of the parallel circuit now, we want to know what happens. Now, what we would have learned before is that in a parallel circuit, the voltage is constant. Good? So it means that the total voltage delivered from the battery power is going to be equal to the voltage across each of the components. That Vt is going to be equal to V1, equal to V2, equal to V3. And therefore the current in the other hand is going to be varying, that due to Kirchhoff's law, that the current passing through the circuit splits at a junction and they regroup at the junction to be the same total amount. So it means that the total current leaving the battery at 6 amps is going to be split up, not it doesn't have to be equally, it all depends on the resistance in the circuit, right? That's a point I want you to know, that the resistance does the current does not have to be split up equally, right? So in this example, that the current is split up, leaving from the battery source of 6 amps. As it goes to the first bulb, it carries 1 amp of current. Then the second one is 2 amps of current. Then third one is 3 amps of current. Good? Now, so we see that the current varies. Now, we want to look at the term resistance. How does resistance tie in a series circuit and in the case of a parallel circuit? In the case of the series circuit, now the resistance, we want to understand how do we find the resistance in that circuit, right? Now, given Ohm's law, which shows the relationship between current and voltage, we're going to see that given that voltage varies, that the total voltage is equal to the sum of all the voltage across each component, and therefore we're going to substitute V into that equation. So we're going to realize that the total voltage is equal to the current times the total current times the total resistance, which is equal to V1, which is equal to the current at component 1 by the resistance at component 1 plus the current at component 2 multiplied by the resistance at component 2 plus the current at component 3 times the resistance at component 3. Good? So that's the new formula that we will introduce today by substituting V for IR, or substituting IR for V, whichever way you state it. Good? Next, we learned that the current is constant. So if you notice here, this current, the total current, is going to be equal to the current at component 1, to the plus, which is equal to the current at component 2, which is also equal to the current at component 3. So therefore, they can all be cancelled out. They could all be eliminated. So once they're eliminated, it leaves that the total resistance, therefore, is equal to the sum of the resistances at each component. So total resistance is equal to resistance at component 1 plus the resistance at component 2 plus the resistance at component 3. Good? And now in the case of the parallel circuit, we want to find out what is the total resistance. Now, same thing. Given that the current varies, we realize that we can rearrange Ohm's law to find out what will be the formula for finding current. And we see that current is equal to I over R. So what it says is since I is equal to V over R, we can substitute that into this equation and we get that V over R total is equal to V over R1 plus V over R2 plus V over R3. And what we would have learned here is that the voltage is constant. And given that the voltage is constant, it means that each of these voltage are the same values, right? So therefore they can be eliminated, which leaves us with that general formula that 1 over the total resistance is equal to 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. So I recommend that you add them as they are there. When you finish adding all those fractions, then you can invert the fraction to find the total resistance, right? Because this formula gives you what is 1 over RT, but what we want to find is just RT. Okay? So, in conclusion, what we looked at today is looking at the relationship between current, voltage, power, and resistance, right? Showing the relation between each of these terms as it relates to electricity. And in there we looked at Ohm's law as it looks at the relationship between the potential difference across a conductor through a conductor, which is directly proportional to the current passing through it. Okay.